In the realm of cycloadditions, we're now going to look at Diels-Alder reaction. And before we begin, I want you to notice a few things. Here on the dienophile we have electron withdrawing groups, which you should know help withdraw electron density to make the dienophile the electrophile in this reaction. Also, take note of the conformation that the diene is in. We can have rotation around the single bond, so this would be an S-cis conformation, and that's needed for the reaction to proceed. Anyway, let's get started. With the Diels-Alder reaction, we're going to have, as you might say, a merry-go-round of electrons. Well, we can start really anywhere we want. I've always tended to start with the diene. Now, one thing you might do before you begin is draw the bonds that you will be creating to form the ring. So what's going to happen here is one of the pairs of electrons from the double bond is going to come up, and that'll form a bond between this carbon and this carbon. In order for that to happen, we need this double bond to move and form the bond there, thus making the electrons here move here. So we have this circle of electrons. So the result isn't too difficult to comprehend, and it's a pretty simple mechanism. If you follow where all the electrons went, we know we have a double bond left here. This bond was created as well as this bond, and we still have the groups we had, the electron withdrawing groups, so make sure we have those. Now the last thing to consider is stereochemistry, because we went from sp2 hybridized carbons to sp3, and I'm referring to the carbons that the electron withdrawing groups are attached to. So, what is the stereochemistry of these two groups going to be? Considering that the starting molecule with the sp2 hybridized carbons was trans, we're also going to see trans here. So if this one electron withdrawing group is on a wedge, the other is going to be on a dash, and of course you would see the enantiomer. And I'll just write EN, the abbreviation for it. A new level of detail, however, is added when we use a cyclic compound as our diene. Because if we consider the Diels-Alder reaction to be a reaction that creates a ring, if we start with the ring, then add another ring to it, we're going to get a bicyclic compound. And then there's another level of detail that we add on top of that. So let's get started. Nothing has changed so far in terms of how we do the mechanism. We can go ahead and start and draw the bonds we're going to create between these carbons, the ends of the diene. Messed up a little bit there. But we'll go ahead and draw our arrows, create our bonds, move this one, and now we're going to have to make a choice. Since it's a bicyclic compound, I'm going to draw it a little bit differently. I'll have this, which is the remnant of what the 5-carbon chain was, and then on top of that we have the 2 added carbons from the dienophile. But before I draw the substituents, you want to consider endo versus exo preference. In this case, we're going to want endo preference because we're getting favorable interactions between the pi bond and the electron withdrawing substituents. So we'll want to put these electron withdrawing groups closer to the pi bond, that one there. And the way we'll do that is we'll put the electron withdrawing groups in what you might consider axial positions based on this view, the way I've drawn it. But the idea is we want to put these electron withdrawing groups here on these positions instead of away from the double bond. So when you start with a cyclic compound for your diene, make sure that you end up preferring the endo product, and also keep track of the idea that you're starting with a ring and you're forming a ring on top of that, resulting in a bicyclic compound.